Hello and welcome to Astronomy 121 tutorial on integration and ordinary differential equations. Here's an outline of what we'll be talking about today. First, I will introduce the notion of an integral and summarize its properties. We'll then go on to talk about the rules of integration, how does one compute the integral of a function, and this will lead us to the discussion of ordinary differential equations. And finally, we'll conclude with some worked examples of actual physical problems. So let's begin. So what is integration? An integral is defined as the area under a curve of some function. For example, I have a plot here. I have the graph of some function, which is this red curve, and I want to know what is the area under this curve. That is the definition of the integral. The simplest way to estimate this area would be to divide my interval, which is in this case is between 0 and 1, into two chunks, 0 to 0.5 and 0.5 to 1, draw rectangles that go through the midpoint values of the function, compute their areas, and then sum them together. Of course, this would be just an estimate, and it's a pretty crude one. But it actually gives us a hint on how to proceed further. Suppose now I will keep subdividing these intervals. As I make them finer and finer, as this width becomes smaller and smaller, you can see that the overall shape of the function is better and better approximated by our rectangles. This is precisely the notion of the integral. It is essentially just the sum of the areas of all these rectangles in the limit in which we make the spacing very, very, very small. So the integral is the area under curve of a graph. Now, it turns out that integration is actually the opposite of differentiation. That is, it is an anti-derivation. What this means is that, in some sense, integration undoes what a derivative does. So the problem of finding an integral of a certain function is really reduced to the problem of finding a function whose derivative is the given one. This may sound confusing, but you'll see what I mean in a minute. And suppose you even figure this out. So you figure out that what the antiderivative of a function is, but now you want to compute this integral to get this number, which is really the area under the curve. In order to do that, you need to make use of the fundamental theorem of calculus, which is that if you have some function f of x, and you have found the antiderivative, which is big F of x, by antiderivative I mean that the derivative of big F of x is the given function, then the integral of f of x dx from a to b is big F of b minus big F of a. This is really, really a profound statement, because what it's telling you is that the area under the curve of f is given by its antiderivative evaluated at the boundary of the integral of integration. In this course, you don't have to prove the fundamental theorem of calculus, but if you ever take a calculus course, it will be proven there. We will make, however, use of this all the time. One should keep in mind the distinction between a definite and an indefinite integral. A definite integral of a function, f of x over some interval, is the area under the graph of f between a and b. This is how we define what an integral is in the first place. So really, a definite integral is a number. An indefinite integral of a function is the task of finding its antiderivative. That is, a new function f whose derivative is the given function. It's curious to note that if you do find an antiderivative f of x, so a function such that its derivative is equal to the given one, then if you take this function and you add a constant to it, the result is still an antiderivative. This is the consequence of the fact that the derivative of a constant is equal to 0. So if you carry out this differentiation, you get two terms, the derivative of f with respect to x and the derivative of c with respect to x. But the derivative of c with respect to x vanishes. What this means that, in fact, if a function has an antiderivative, it has an infinite number of them, all differing by this constant. This is precisely the origin of the constant of integration. practically, this amounts to always remembering constant integration whenever you write down an indefinite integral. So always, 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 if you have an integral with no bounds, the result will be some function plus a constant. Alright, so suppose we actually want to compute the integral of something. We figured out that if we had the antiderivative, then we can use the fundamental theorem of calculus to achieve this goal. So, of course, our task is to compute the antiderivative. How we would go about doing this? Suppose we start with a simple function, x squared. So what we really want, if we want to find the antiderivative, is a function that when differentiated would give us x squared. The place to start is to remember our rule for differentiating powers. d by dx of x to the n is n times x to the n minus 1. So notice that if we get that the antiderivation is x cubed, and we carry out the differentiation, we get 3x squared, which is not quite x squared, but very close. And it guides us towards the right answer, because now if we take our initial guess and we simply divide it by 3, and we carry out the differentiation again, we do indeed get x squared. Try this for example, f of x is equal to x cubed, x to the fourth, x to the fifth. Do you notice a pattern? In fact, for any x to the n, the integral of x to the n dx is x to the n plus 1 over n plus 1 plus our constant of integration. This is easy to check by taking this expression and differentiating. So what other rules of integration do you need? I will not prove these, but you should know them. Here are the most important ones. The integral of a constant is that constant times x. That's constant integration. We should know the integral of sine, the integral of cosine, the integral of 1 over x, and the integral of the exponential. So please make sure you simply memorize these if you haven't already. Let's move to differential equations. So how does physics come into all of this? So in physics, we study the laws of nature, and our study frequently leads to an equation which involves the variation of time of some quantity of interest, for example, position, or velocity, or density. Of course, the variation with respect to time is nothing else than the time derivative of this quantity. An equation such as this is something we call an evolution equation, and if we know how to solve it, then it tells us how a quantity of interest changes with time, which is exactly what allows us to make predictions about natural phenomena. This is a special case of a differential equation. Intuitively, a differential equation is just an equation which involves derivatives of some function. We will see an example shortly. So here's our first example of a differential equation as applied to a physical problem. Sir Isaac Newton studied a lot of different things, and one of them was examining how objects cool. And he proposed that the rate of change of the temperature of an object, so the rate at which it cools in a colder environment, is proportional to the difference between that object's temperature and the temperature of the environment. In mathematical terms, that's translated, that means that the time derivative of the temperature, this symbol means proportional to the difference between the temperature of the object and the temperature of the environment. We want to make this an equation, not a proportionality, so we need to put in the constant of proportionality there. One thing we should note is that the object is cooling. If you think back, you know that if an object is cooling, that means that the temperature is decreasing, and that the derivative of a decreasing function should be negative. Since t minus ta is positive, because t is the temperature of the object, and we said we start with an object which is hotter than the environment, that means that t minus ta is positive. So in order for d by dt to be negative, we must put in a proportionality constant minus k, with k being equal to 0, and being greater than 0. So this is the differential equation that we would want to solve. And it describes the change with respect to time of a temperature of some object. Let's go on and try to solve it. So, here's the statement of the problem. What is the solution to this differential equation with the initial condition the temperature at time equals to 0 is equal to T0? This is very important. The initial condition is what allows you to actually pick out a single solution to a differential equation from infinitely many solutions, all different by a constant. Precisely that constant of integration that I talked about before. Let's see how this arises. I find it convenient to introduce a new variable, which is equal to t minus ta. Now I need to relate the rate of change of u to the rate of change of t. To do this, I simply differentiate both sides of this equation and keep in mind that ta is a constant, so its derivative will go to 0. And then I find out that du by dt is actually equal to capital T by dt. So I put this expression back in my original equation here. So the equation I now am interested in is du by dt is equal to minus ku, which is a simplification in my eyes from what we started with. This is an example of what we call a separable equation. In a separable equation, we can put, so to speak, everything with the dependent variable, in this case u, on one side, and everything with the independent variable on another. So if I divide both sides by u, I get 1 over u du is equal to minus k dt, where I cross-multiply and put dt on the other side. The idea is now to integrate the left side with respect to u and the right side with respect to t. Of course, strictly speaking, what we really mean to do is simply divide both sides of this by u, and then integrate this expression, both sides, with respect to t. However, it turns out that if you try to carry out the integral on the left-hand side, that will be equivalent to doing 1 over u du, just a technical point. We will stick with this expression here. So we have separated variables successfully. We have everything with u on this side, everything without u on the other side. Let's carry out our integral. Now, if you look at our rules of integration, the integral of 1 over u du is just ln u. The integral of a constant, which in this case is minus k, is simply minus k times t. And then I put in our constant of integration. The way to proceed now is to exponentiate both sides. The exponent of ln of u is simply u. Then I will have a term e to the minus kt times e to the c. If I introduce a is equal to e to the c, I have a solution to my differential equation, which is u is equal to ae to the minus kt. Am I done? Well, not quite. First of all, I didn't want to solve for u. I wanted to solve for t. So I have to go back to my definition of u and actually rearrange it for t, and then plug in my expression here. And that's very easy to do, and you get that t is equal to ae to the minus kt plus ta. I'm still not done, because I don't know what this constant a is. To evaluate this constant of integration, I need my initial condition. I told you that at time t is equal to 0, the temperature is some temperature T naught. So if I take this value and I plug it in here, and I plug 0 for the time, I get T0 is equal to ae to the minus k times 0 plus Ta. Now, e to the minus k times 0 is e to the 0, which is 1. So what this really is saying is that T0 is equal to a plus Ta, which I, of course, can immediately solve for a, which is equal to T0 minus Ta. Finally, then, if I take this expression for a and I put it in here, I get the correct solution to this differential equation. And you can check this, as usual, by differentiating with respect to time and making sure that the left-hand side is equal to the right-hand side. Instead of using this constant of integration here, I could have gone about doing the integration in a slightly different way. What I could have done is, instead of using indefinite integrals, I use a definite integral and use my initial condition in the bounds of integration. So in this case, I would integrate the left-hand side from some initial value of u, which I called u naught, to some current value u, and I would integrate the right-hand side from the initial time 0 to the current time t. Since this is a definite integral, I have to make use of my fundamental theorem of calculus. So I get ln of u minus ln of u naught, and on the right-hand side I would get minus kt plus k times 0, which is just 0. So on the right-hand side, I would just end up with minus kt. To rearrange this equation, I need to remember the logarithm rules, in particular that the ln of u minus ln of u0 is ln of u divided by u0. On the right-hand side, I still have minus kt. If I now exponentiate this, I would get u over u0 on the left-hand side, and e to the minus kt on the right-hand side. Cross-multiplying and substituting u is equal to t0 minus ta will give you the final answer. Alright, let's go on to another example. In this case, we'll actually need to formulate the differential equation we need to solve. Suppose that I have an object, such as a ball, which is moving through a viscous fluid. So the fluid is actually slowing down the object. So something like a ball moving through honey. And I want to write down and solve the differential equation describing the variation of the object's velocity with time, given that initially its velocity is some number v0. To proceed, we actually have to use some laws of nature, in particular Newton's second law, which says that the force on the object is equal to its mass times acceleration. Remember that the acceleration is nothing else than the derivative of the velocity with respect to time. We're also given that the drag force is proportional to the velocity squared. So why did I write f drag is equal to minus kv squared? Well, here k is the proportionality constant, which I assume to be positive, and the minus sign is because the drag force would always be directed in the opposite direction to the motion of the ball, because the drag force slows down the ball, not accelerates. Now, in reality, this k is not really a constant for all possible bodies in all fluids. It depends on the fluid density, the area, the object we're considering, etc. But for the time being, let's ignore all of these problems and treat k as a constant. Now, if we assume that drag force is the only force acting on the object, I can tell you that it is, then we have that f drag is equal to ma, which is m times d by dt. If I set that equal to this expression here and divide both sides by m, I finally end up with a differential equation that we want to solve. So let's go ahead and solve it. Our approach is again the same. We use separation of variables. So we put everything with a dependent variable on the left-hand side, everything without on the right-hand side. So here we would get 1 over v squared dE is equal to minus km dt. We now integrate both sides. The integral of 1 over v squared is minus 1 over v. This is nothing else than our usual rule for integrating x to the n for the case where n is equal to minus 2. On the right-hand side, we're again integrating a constant, so it's no surprise that we get that constant times time, and we must not forget our constant integration. So we have this solution for v here. We're not done yet, because we don't know what our constant integration is. Again, we use our initial condition, which means that I plug in the initial value on the left-hand side, I set time equal to 0, and I solve for my constant integration, which is easy to do in this case. And the full solution, if you just put this c here, is given by this expression. And if you do some algebra, which I'll leave as an exercise, you end up with a form like this. Now, once you're done solving this, you should ask whether this solution makes sense. Well, we expect that the drag force slows the body down, so that as time goes on, our solution should tell us that the velocity is decreasing. Well, as time increases, this term will grow, so the denominator of this expression will grow. This term is constant, so we'll be dividing by a larger and larger number, so the velocity will indeed decrease, as we would expect. And as usual, always do this. Take this expression, differentiate it, put it back in the differential equation, and make sure that we solve it correctly. That is all, and thank you for listening.